All right, so in this video, I'm going to be breaking down the exact thought process which led me to find a cross-contract reentrancy vulnerability, which ended up paying nearly $1,000 in rewards. But before I go through the code and the actual finding, I'll first just give you a bit of context on the code base and the important contracts involved. So all you really need to know is that the protocol allows leverage traders to deposit a collateral token and then open leveraged long positions on that same token. And if you don't know much about leverage trading and perpetual futures, it shouldn't matter. You'll still be able to follow along with the finding. So now let's look at how these traders can actually create these positions. So the first step would be they call this announce leverage open function on the delayed order contract, which is just a user-facing contract which is meant to allow users to announce the different actions they want to make. So in this case, the user is going to announce that they want to open a leverage position. And then the second step would be after a certain delay period, so 120 seconds in this case, a bot called a keeper, which is run by the protocol, will actually execute the order. So it takes 120 seconds from the user announcing the position to be created until it's actually created. And during the second transaction here, the delayed order contract actually makes a call to this other contract, the leverage module. And this, it calls the execute open function. And this pretty much mints an NFT to the user as proof of the position that they've just created. Now the vulnerability actually ended up lying in this execute open function. So now I'll explain the thought process which led to me finding it. So if we go to the code here, this is that same execute open function. So it's going to be called by the delayed order contract, and it's in the leverage module contract. So we'll just go line by line from the start, but I'll skip most of it because the start of the function is fine. So these comments, by the way, are what I was actually putting in during the audit. So I just go line by line, and when I think the code is good, I just put this comment in so that I don't have to accidentally go and read it again. So if we just go by line, everything is looking fine. I have these good comments on them. So everything's good so far until we get to this line. So it calls the internal mint function. So let's just see what that does. Okay, so that calls safe mint. So if you're familiar with how safe mint works and how it's different to just normal NFT minting, you'll know that it actually makes an external call to the to address. But if you're not familiar with that, I'll just go into it. So it calls this check on ERC721 received function. So it first just mints the NFT as normal, but then it also calls this function. So let's see what that does. So here we can see that if the to address is a contract, it makes this external call to that to address. So it calls this function here on the to address. So okay, if we go back to the function in question now, okay, we're at this line again. We know that it makes an external call to the account here. So that's not immediately an issue. In order for a reentrancy attack, we would need certain state to be not up to date when this external call is made. So the next step, which is what I did during the audit, was I just figured out, okay, what state is not up to date when this external call is made? So another way of putting that is what state changes have been made after the external call. So I just tried to list out every state change which happens in this block of code here. So this is what I ended up listing. So pending state updates, so state that hasn't been updated yet, includes this piece of state, so this mapping, and this variable, and also this variable in a different contract. So now we just have to go through each of these and figure out if we can exploit the fact that when this external call was made, the state of this hasn't been updated yet, which means that when we re-enter, we can enter the contract in a way, or enter the entire system, maybe not the same contract, in a way where this is not up to date. And potentially that could lead to an issue, but not always. So now let's look at the actual piece of state that's not being updated, and let's see if we can exploit it in some way. This state mapping in the vault contract is updated through calling this function. Let's just see what it does first. So all it does is it sets a certain value in the mapping to this new position. And the new position is just a struct which contains all this information. So if we think about re-entering this function when the external call is made to the user, this hasn't happened yet. So that means this assignment didn't happen. So the value of this would just be the default value of any mapping. So the value of positions at that token ID is just going to be a struct, a position struct with all 0 values. So now that we know we can re-enter the contract with the position struct being like this rather than being filled out, we can look at where that position struct is accessed and see if we can somehow exploit it somewhere in the system of contracts. So let's look at this positions mapping and see where it's being used. So is it being used in this contract at all? No, it's not. And it's internal, so there's got to be a getter function somewhere because it must be used externally. And yeah, so that's the getter function for the positions. So now let's just search globally for this get position function. So this is the first instance of the get position function being called. And we know that if we re-enter the function, this is going to be an uninitialized struct in a mapping. So that means that this is going to be 0. This field is going to be 0. And that means this entire value is going to be 0. But I won't get into the details, but we actually can't exploit anything here in this function because the 0 values are going to lead to a revert. But so anyway, we'll keep moving on. And it's being used again, in this case, to close the position. And we could technically try to re-enter and immediately close the position, but there's nothing to gain from that for the user. And it might actually revert in one of these checks as well. But I won't go into that now. I'll just go into where the vulnerability actually was. So I just kept going through each of these, looking for where the get position function was being called. So in this entire leverage module, we can actually ignore the usage of get position since we won't be able to enter any of these functions. We won't be able to call them ourselves since they're only allowed to be called by the delayed order contract here. It can't be called by any other user. So I can just skip all of these. Okay, so now we're in this new contract called limit order. Again, the get position function is being called, and we're checking the additional size field, which is just an integer. So we know that this entire thing is going to be 0 if we called this function by re-entering at the mint call. So let's see if there's any benefit here for the user. So there's a 0 here, and that's being passed in to this get trade fee function. The trade fee is being calculated with an additional size being 0. And it turns out, if we look into that, it simply multiplies the size of the position with a certain value. But since the size that we pass in is going to be 0, this entire thing is going to be 0. And that means that this trade fee value that's calculated is going to be 0. So we know that we can call this announce limit order function, and the trade fee is going to be 0. And we don't have to go through the entire function, but it actually doesn't revert. So even though the position hasn't been created yet, we're able to create a limit order on that position. And the trade fee is going to be zero, even though the position we created actually does have additional size, but it just hasn't been updated yet when we re-enter the system. So in the end, the issue is, or the vulnerability is that a user can use cross-contract reentrancy to create a limit order which ends up having zero fees. And that's because of a certain piece of state not being updated before the external call. It's being updated, but it's being updated after the external call is made. So we can exploit that by re-entering during the external call. And you can see how there's a pretty methodical approach you can use to find these. You just first look for the trigger, which is state being changed after an external call being made. And once you've spotted that, you can just search for all the different areas in the code where the state is being used and see if you can use that state while you're re-entering the function at this point, or re-entering the system, I should say, at this point, and then somehow, exploit the contract in some way they don't intend.